And this is something I actually just learned like a year or two ago, which I have taught pre-calculus for a long time. I don't even know, this was not in our regular pre-calculus material, but I didn't even know about this until just a little bit ago. Whenever I learned it, I was like, how did I not know about this? Why didn't I not learn this somewhere? So this first part I know, the second part's what I didn't know. So we're going to talk about rates of change specifically in linear and quadratic functions. So linear, I definitely already knew this. For any linear function, the average rate of change over any length input value interval is constant. So your rate of change for a straight line is constant. It does not change anywhere on that line, no matter whether you're looking at average rate of change from 0 to 1 or 2 to 7 or -10 to -5,000, or I guess the other way, -5,000 to -10. The slope's always the same. Okay, this is often, this note right here, we often think of this as the slope of the line, and we should have a lot of experience with figuring that out. Okay, so you do this even some in Math 1. You talk about a constant rate of change. So example 1 here says the table above gives selected values of the function f of x. Explain why f of x is not linear. Okay, so who could tell me here why this is not linear? What do you think, Tyler? Okay, so the x is not going up at a constant rate, but the f of x is, right? So a lot of times we might start looking like, oh, this goes up by 3, up by 3, up by 3. Oh, yeah, that looks linear. But over here, we're going up by 1, up by 2, up by 4, right? So if we are looking at our slope for that, it is our change in y over change in x. If I use that delta before, that triangle. That triangle is delta, it means change in. And so the change in y was the one on this right side. It was 3 over 1 for this, between these first 2 points, right? But then for the next one, my change in y over change in x is 3 over 2. And then for the last one, my change in y over change in x is 3 over 4. So we could say something like the average rate of change is not constant. So whenever you're looking at these tables, it's important to look at both your x and your y to see how they're changing, not just the y value for that. Okay, so for linear, your rate of change should just be the same number all the time, right? You should get, the same rate of change between any 2 points on the graph. Let's look at what happens with quadratic. And I did not know this before a couple years ago when we had a training on something. So we've got g of x equals x squared. They ask us to complete this table of values for g of x. So when I'm completing a table, all I'm doing is plugging that number in, right? So like when I have -3, it's really just asking me to find g of -3, which means I'm just plugging -3 into my equation, which is a very simple equation, -3 squared. -3 squared is 9. Right, I'm not going to write that out for all the rest of these. -1 squared is 1. Positive 1 squared is 1. 3 squared is 9. 5 squared is 25. Okay, so they ask us to look at the average rate of change for all of these intervals from -3 to -1, -1 to 1, 1 to 3, and 3 to 5. Okay, so when I have a table, the way I like to do average rate of change, you can do like -3, 9 is 1 point, and -1, 1 is 1 point, and you can do slope formula, right? You could do 1 minus 9 over -1 minus -3. Did I do that right? Yeah. And I will get -8 over, that'll be a +2, and I'll get -4. So -4 will be my average rate of change. Okay, so you could do points. I think with tables, it is a lot faster. Like if I'm looking at this next one from -1 to 1, I'll usually just like to do this from 1 to 1. How much did that change? None, 0. And then from -1 to 1, that would be up 2, right? So my rate of change here would be 0 over 2, which is just 0. And then for the next one, from 1 to 3, I just like to look at what happened here. I went from 1 to 9. That was up 8. I'll make sure you're considering whether you're going up or down. If you're going up, you need a positive. If you're going down, you need a negative there. Up 8, and then here I went up 2. So my rate of change for this section is 8 divided by 2. So I'll just get 4 over here. Okay, and then the last one, I got to go from 9 to 25. So we'll see, 25 minus 9 is going to give me 16. And then right here, I just went up 2. That one's the same all the time. So I've got 16 over 2. So I'll get 8 for my average rate of change on that interval. Okay, so what do you notice about these average rates of change? Let's pay attention to the wording of this too here. What do you notice about the average rates of change of g of x over consecutive equal length input intervals? Okay, we're just going up 4 each time, right? And that consecutive equal length input intervals is important because you have to be going up by the same amount on your x's to make this conclusion. If your table went from -3 to 0 to 10 to 25, then you could not really make a conclusion using this information. But if you're going up by the same amount and you're not skipping any intervals, then what we see is that this average rate of change it increases by 4 for every interval. That we look at. So what that means, if I think of doing the rate of change of the rate of change, I'm going up 4, up 4, up 4. What type of rate of change is that if it's always 4? That would be constant, right? What happens if something is quadratic, the rate of change of the rate of change is going to be constant for that. So this asks us, it gives us selected values of functions, and we're supposed to determine if the function could be linear, quadratic, or neither. So let's look at it. It's important to look at your x's first. This one's going to be easy because what do your x's do on A here? They go up by 1 each time. So that makes it a little bit easier because whenever you're doing your rate of change, it's just going to be over 1, every one. So we go up 1, we go up 3, and we go up 5. Okay, is it linear? No, because if this was linear, I would get the same number for my rate of change each time. And since I'm going up by the same amount, I don't even really have to do the rate of change. I can just look and see if I'm getting the same number each time. So this is not linear. What you want to do to check to see if it's quadratic is look at the rate of change of your rate of change, which means take these numbers that you got right here and see what they're going up by. From 1 to 3 goes up by 2. From 3 to 5 goes up by 2. Is that constant? Yes. So this sometimes is called your second difference. Like this would be your first difference. It's how much you're going up by each time, the difference between the two values. If that is constant, then you have a linear function. If the second difference is constant, you have quadratic. So this would be quadratic. Now, I do kind of like the guy who makes these notes is much more precise than I sometimes am. He doesn't say, I lost my C there somehow. He doesn't say which one is linear, quadratic, or neither. He said which function could be linear, quadratic, or neither. This function could be quadratic. Why do they not say it is definitely quadratic? Exactly. The chart could change, right? We don't know that 5 is going to necessarily be 16 or whatever we need for, I think it'll be 16 for that. We don't necessarily know that's going to happen. It could start going back down. It could do something crazy. We also don't know what's happening between 1 and 2. It could be like 1.5, could be like 2,000 for all we know, right? So charts are never going to guarantee that something is the case, but certainly this is consistent with being quadratic, so it could be quadratic here. All right, so let's keep going. This next one, our x values do not increase by a constant number, so we have to pay attention to that. So we're going up by 1 here, we're going up by 3 here, and we're going up by 5 here. Over on this side, we go up by 1, up by 3, up by 5. So if I'm doing my rate of change for this, over here I didn't even really have to consider rate of change so much because I was going up by the same amount each time. Over here it matters, so I've got to do change in y over change in x. So for that rate of change, or average rate of change, I guess I should say, then I've got to do 1 divided by 1, which is going to give me 1 for that, between those two. Then I would do 3 divided by 3. It's always the 1 over here on the right divided by the 1 over on the left, because it's your change in y over change in x. That is also 1. And then this I've got to do 5 over 5, which also gives me 1. So that average rate of change for each one of these intervals is always 1. That means it's constant. What does that tell us this graph could be? Linear. This one's linear. Okay. For this last one, we are going up by 2, up by 2, up by 2 on my x's. So since my x's increase by equal length intervals, consecutive equal length intervals, to use the language that AP likes to use on this, I don't really have to worry about doing that division, because it's going to be divided by the same number each time. So in order to have like a constant rate of change, I'd have to have the same number over here as well. So if I look here, from -1 to 1, that goes up 2. From 1 to 2, that goes up 1. And then from 2 to 2, that goes up 0, right? Or probably shouldn't even put that plus sign there. It doesn't go up at all. So is it linear? It is not, because that number should be the same every time if this was linear. So I want to check my second difference on this one. So 2 to 1, that goes up 1. From 1, oh wait, no, it doesn't go up 1. What does it do? It goes down 1. And then from 1 to 0, down 1 again. Is that constant? Your second difference is constant here. What does that tell us we're dealing with? Quadratic. And he didn't put a neither example here, but a neither example would be like, for example, if this was a -2 right here, then that would go, instead of going up 0, this would be down 4, which means that here you'd be going down 5, and you would see that as not a constant number. So it would not be quadratic, it wouldn't be linear, so you would say neither for that one. If you don't see a constant rate of change either showing up in the first time or the second time, then that would be a neither. Okay? Let's talk about concavity. For concavity, the average rate of change over equal length input value intervals is blank for all small length intervals. So our rate of change, or our average change over the interval, over equal length input value intervals, this is looking at your average rate of change over those, right? It is going to be, when we're concave up, our rate of change is increasing. I don't know why it's highlighting those things as I write them. So think about positives, easier for me. Rate of change, you got a little tiny rate of change, and then it gets steeper, and then it gets steeper, and then it gets steeper. That makes it concave up, right? So that would be increasing. So if you have something that's concave down over equal length intervals, your change is going to be decreasing. So one thing that I'm going to ask you about this is I'm going to give you a table, and I'm going to ask you to tell me whether this would be quadratic, linear, or neither, right? Another thing I might ask you is I might give you a table, and I might ask you to tell me whether this is concave up or concave down, or could be concave up or concave down. So if we look at all three of the tables that they have given us here, we are increasing by equal length intervals, right? We're going up by 0.1 and up by 0.1 and up by 0.1. If that was not the case, then I'd have to actually do the rate of change and pay attention to that. But since they're all equal length intervals, I can really just look at my change. So from 4 to 1, that is down 3. And from 1 to -1, that is down 2. And from -1 to -2, that is down 1. And this is my average rate of change, if we want to label it there. So this rate of change, is it increasing or decreasing? Increasing. I want to say decreasing because you're going 3, 2, 1, but they're negative, so -3, -2, -1 is increasing. So if my rate of change is increasing, then my graph would be concave up. Your rates of change are negative, but increasing. So your graph is a decreasing graph. Your graph of K would be a decreasing graph that is concave up. So it would look like this, if you think of like graphing it. Here. Okay, B, let's look at our change. We got up 3, up 3, up 3. Okay, this is our easiest one, kind of. Is that concave up or concave down? Neither one, right? Because your rate of change is not increasing or decreasing. You just have a straight line here, so it wouldn't be concave up or down. So this would be neither. And then if we look at this one, we go up 6. That'll be up 4. And this one's up 2. So would your rate of change be increasing or decreasing here? Decreasing, which means we would be concave down. So let me ask you this question. which one would this graph look like? This top part or the bottom part? Top, because our rates of change are positive, which means our graph should be increasing, but the rate of change is decreasing, which tells us concave down. So this is increasing, but concave down. So it would look like this here. If I had like -2, -4, -6, that's what we'd be looking at here for that. Okay. Two things from those notes that you will be looking at. You'll be looking at whether it's linear or quadratic and whether you're concave up or concave down. In an ideal world, we would pause here and I'd give you some to do. But because tomorrow's kind of messed up with the speaker and possibly my absence, we're going to keep going to 1.4 today. Let me give you guys these. Where's that one? Don't save it. I think we're gonna get through this. I think we can do it. Okay. So we are now going to look at polynomial functions and rate of change. That's what AP calls this this particular section. Honestly, I don't think we're doing a whole lot with rates of change here, a little tiny bit, but that's what they call it. So I'm just using the straight titles that AP gives us so that we're all kind of on the same page. So polynomial function. You work on this in Math 3. Okay, so this should be a review for you, although I understand some of you, it's been a long time since you had Math 3 and you've probably forgotten some of these things. But hopefully it'll be at least a little bit familiar to you. So I think pretty much everything we're doing today should be a review for Math 3. It's not really anything new that you should be seeing. Now what you might be saying, Miss Hyatt, I've never seen anything looking like this crazy stuff in the middle in my life. This looks ridiculous. It's good to learn how to read this notation right here, so I'm going to spend just a minute on it. We have P of x equals a sub n, x to the n power, plus a sub n minus 1, times x to the n minus 1 power, a sub n minus 2, x to the n minus 2 power, plus ... and so on, until we eventually get to a sub 1 times x plus a sub 0. Okay? So let's look at some different parts of this. Use my highlighter here. Let's look at the variable parts first. Highlight right behind there, even though there's nothing there. All right, so n is some sort of number that we might have. It might be 10, it might be 4, it might be 2. It is, in this particular case, greater than 2. Well, really, it's got to be pretty big because you got to subtract a bunch of times. But whatever your number is here, what do you know about the exponent on the next term? So, like, let's say this n right here was 7. What would the exponent on the next x be? It'd be 6. Because it'd be n minus 1. And then we'd have 5, right? Because it'd be n minus 2. So 7 minus 2 would be 5. And then we'd have 4. And then we'd have 3. And then we'd have 2, 1. And back here we would have 0. But x to the 0 is just 1, so it goes away, right? So all this right here, this n minus 1, n minus 2, blah, 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 all that's telling you is your x's are in descending order, right? You might have x to the 5th, x to the 4th, x to the 3rd, x, squared x to the first. We call this standard form, right? Because whenever you're writing a polynomial in standard form, you are going to put your highest exponent first, and then the next one, and the next one, and so on. So that's all it's telling you here with that crazy notation. Then, for this part here, you have a's, and you see the same thing happening. And these aren't exponents, right? They are just like subscripts there. And so all that's telling us is like the first A and the second A and third A and fourth A and so on. So you notice that you just have different A's here. So some things that you need to know. Something you may be asked for is going to be the leading term. The leading term in this case would be A sub n x to the n power. It is the term with the highest exponent, right? This right here would be your highest exponent. And you may remember from Math 3 that we call that highest exponent in a polynomial function the degree of the function. So the degree of this function would be n, whatever your highest exponent is. If that is 7, you have a 7th degree polynomial. If it is 3, you have a 3rd degree polynomial. And your leading coefficient is going to be the A sub n that you see right here. So that would be A sub n. It's the number in front of your x. So your degree is that n. That is just your highest exponent. And the A sub n is the number in front of the x with the highest exponent. Right? Mathematicians love this sort of notation. Math students usually want to just know, just tell me it's the highest exponent. Don't give me this crazy formula, right? Degree is your highest exponent. Leading coefficient is a coefficient is the big number in front of your variables, right? It's the number in front of your variable that has the highest exponent. So, for example, if I look at A, my leading coefficient would be 3. My degree would be 4. Now, for A, 3x to the 4th is your first term. So, B is my leading coefficient 12. It is also not 7. It's almost 7. You got to keep that minus that right there with it. It should be negative 7 for that. And then what would the degree of that one be? 3. So, if it's written in standard form, it's going to be your first term. But it might not always be given to you in standard form. So, you got to search out the highest exponent. Your leading coefficient is the number in front of that variable with the highest exponent, and then the exponent is your degree. Oh, what about C? It's so easy, it's hard. Leading coefficient would be 4. What's your degree? It's 0. Because I could put x to the 0 power out here behind this, and x to the 0 power is just 1, so that'd be 4 times 1, which is just 4. So there are no x's in that, so it has a 0 degree. Okay, and we're going to talk more about what these degrees and coefficients show you about a graph of a function. Okay, all right, so let's talk about extrema. Okay, the extrema are going to be your maximums and minimums of a graph, but you should hopefully remember from Math 3 that there are 2 different types of maximum and minimums. So there are 2 types. Okay, and those 2 types are relative or local. These 2 words right here, relative and local, are used interchangeably. They mean the same thing. Some textbooks use the term relative, some use the term local. AP is going to use both, and they're going to use them interchangeably. They don't usually use the same one like in the same problem, but, you know, question number 7 might ask for a local maximum, and question number 10 might ask for a relative maximum. They're asking for the same thing, but they're just using different terminology. So we need to be familiar with both of those. Same thing for absolute and global. I prefer relative and absolute. I think that was probably what I was taught at the beginning. Plus, I like absolute because it just makes sense. But we're going to talk about the differences for these two. So a relative extrema. I also have to note there's a major controversy about this definition right here in the calculus teacher community right now, in the AP community, because it says a polynomial has a relative minimum or relative maximum where it switches between decreasing and increasing, or at an endpoint if the polynomial has a restricted domain. Okay, the major controversy is in parentheses at the end of that definition, and this is very. I mean, I kind of understand why it is. It's because of the way they have used the definitions. In calculus, you can't have relative max or minimums at the endpoints. You can have absolute, but you can't have relative in calculus. They have defined this so that in pre-calculus, we can have relative max or minimums at the endpoints. So when I first looked through this, I was getting some of them wrong because I was using what I have learned in calculus, and I do think they're going to avoid asking the endpoint questions on the exam because of that reason. Now, our work is going to have some of those endpoint questions, but I think they'll avoid asking it on the actual exam. So relative maximums are most of the time going to be the places where you switch from increasing to decreasing or decreasing to increasing. So, for example, right here would be a relative maximum point. Right here would be a relative minimum. And right here would be a relative maximum. We'll talk about that in a minute. That might seem a little wrong, but it's true. We've got an arrow on this end. This point right here, this is the one that would be different. In calculus, I would not call that a relative max or minimum. But in PreCal, this is a relative minimum because it is lower than the points around it. Now, you might be thinking, like, I'm not so sure about that, Ms. Hyatt. Are some of those not absolute? All, except for input, well, really, I guess with this definition, all absolute could also be relative for that. Because our definition here is telling us that we're switching from increasing to decreasing. So it is definitely true that at x equals 3, we are switching from increasing to decreasing. So that is a relative maximum. It is also an absolute maximum. It is both at that point. For that. But this only asks us about relative maximum. So whenever you report these, your local maximums or minimums, notice it says local minimums at x equals, so you're only giving your x coordinate for this. So your local minimum at x equals, the minimums are at x equals -4 and at 0. Okay, good. Because at this point we're looking at the x values of those points. It's really tempting to say you've got a relative minimum at -1, particularly for that middle one, but you're given the x coordinates. You have local maximums at -2 and 3. X equals -2 and 3. For that. Okay. Questions? Okay, so a local, of all of your local maxima, The greatest is the absolute maximum. Same thing for minimum. Of all of your local minimum, the least of all of them is your absolute minimum. So every time your absolute maximums or minimums are also relative maximum or minimums. So, for example, this is the same graph that we have over here. So if I'm looking for my absolute maximum, I'm looking for the very highest point. That is right here. So that point is a relative maximum, but it is also my absolute maximum because it is the highest point on the whole graph. Now, to report this, notice that they give us like a little bit of we have absolute maximum equals at x equals. So if you ever have a question that says, what is the absolute maximum of f? The absolute maximum is the y coordinate. The maximum is the y coordinate. So we're going to say the absolute maximum in this case would be 2. It is the y coordinate. There's my maximum. It occurs at x equals 3. Usually with relative maximums, they only ask you for where it occurs. They'll say give the x coordinates where you have a local maximum or minimum. With absolute maximums or minimums, a lot of times they will ask what is it, and then you're given the y value for that. What is the absolute minimum on this? What do you guys think? This one, the -3? Yeah. That is what I wrote down on my paper whenever I was doing this. And then I looked at the key and I realized that is wrong. This is not your absolute minimum. Does anybody know why? It does not have an arrow here. Where does it have an arrow? What way is that one pointing? Down. So if you continue on here, that's going to keep going down forever. And since that goes down forever, it goes down to negative infinity. Are you going to have a minimum for that? You will not, because one side of the graph goes down forever. So if you have a graph that goes up forever or down forever on either side, then you're not going to have that maximum or minimum point. So that one was tricky. I was kind of glad it was thrown in there because it got me. I was thinking just like Lucas, right? Yeah. Yes. Lucas Hampton. Lucas Keller is in the same seat in third period. You were Lucas Hampton. Okay. Just like he was thinking, I was looking at this point right here. I thought that was the lowest point, but it is not because of that arrow on the end. So if I had had a dot over here on this end, it would be our minimum. So we would just say none for this. There's not one. Let's see. I'm just going to let you guys do these next 3 on your own. Do these next 3 on your own and see how you do with them. Relative minimum. So that also means there's no relative absolute minimum either. Relative maximum at x equals 1. When we say absolute maximum, we say it's at, it equals 3, and it happens at x equals 1. Everybody good there? All right, here's the next 2. Did you guys get none for the absolute minimum? That one tricks me because it doesn't. If you don't pay close attention to that arrow, you don't. You just kind of are looking around. And you're like, oh, lowest point right there. So you gotta be careful with that. But -2 for your minimum, -4 and 3 for your relative maximums. No absolute minimum. Absolute maximum is 2. It happens at x equals 3. And then an important thing to note about this, if you have dots on both ends, if you have a continuous function with dots on both ends, you have to have an absolute maximum and absolute minimum because that graph stops. So there has to be a highest point and a lowest point. If there's arrows, that's not the case, but we have to have absolute maximum and absolute minimum. So relative minimums at -3 and 3, maximums at -4, 0, and 5. And then your absolute minimum would be -3, and it happens at -3. Absolute maximum 4, and happens at x equals 5. Okay, questions? All right, so some fun facts about polynomials here that we have to know. Between two real zeros of a polynomial, somebody remind me, what is a zero of a polynomial? Where it crosses the x-axis. It's our x-intercept of a polynomial function. So between any two x-intercepts, so we're thinking about, like, we've got a graph, and between any two places where it crosses the x-axis, no matter what it looks like, if it is a continuous function, you've got to either have one relative maximum or a relative minimum. If you think about what's happening there, you're at this x-intercept, you got to get to the next one, and polynomials are never going to be constant. They're not going to have just like a straight stretch in them. They're always going to be curved. So you either got to go up and back down to hit the x-axis, or you got to go down and back up. So you're going to have a relative maximum or minimum between every set of zeros that you look at. Polynomials of even degree. So if it is a second degree, fourth degree, sixth degree, eighth degree, and so on, they must either have an absolute maximum or an absolute minimum. And I could use the word, I think I meant to use local and global there. That's why it has an A instead of an. Just to mix it up. You can use either one of those words right there. But even degree, we're going to talk more about in behavior later, but, like quadratic, it's either going to look like this or this. Both ends of the graph are going to go in the same direction. So you have to have an absolute max or absolute min. Fourth, sixth, eighth degrees, they have that same property there. All right, let's see. Is this our last page? Okay, we can do it. We got 12 minutes. All right. Points of inflection. Points of inflection occur when a function changes from concave up to concave down, or from concave down to concave up. So it's where your concavity changes. At a point of inflection, the rate of change of a function changes from increasing to decreasing, or from decreasing to increasing, because we've used that chart several times. Like if I have a function and a rate of change of that function, right? If I'm concave up, my rate of change is increasing. If I'm concave down, my rate of change is decreasing. Right, so if I switch concavity, then I'm going to switch, my rate of change is going to switch from increasing to decreasing, or vice versa. So this gives us a graph here, and it first asks us to find any points of inflection. In my opinion, it is much easier to find maximum minimum points on a graph than it is points of inflection. Because you feel like there's a little gray area, like, for example, definitely we're concave up over here. And this middle part is concave down, right? And then we go concave up again. Now, it might be a little less obvious exactly the point where you switch. So these questions, a lot of the homework might be open-ended where you've got to just tell me something, but I'm going to make them multiple choice on a quiz where you don't have to, it's more obvious what they are. So definitely somewhere in here and somewhere in here, we are going to switch concavity. And so I would go with, I think these points right here are probably going to be the place. So we would have points of inflection at x equals -1 and x equals +1.
So a point of inflection is where it changes?
Where you change concavity, yes. So like right here we're concave up, and again right here we're concave up, we're like curved up there. Here in the middle, our graph is concave down. So it's the place where it switches. Okay, so it says for each of the following intervals, we're supposed to determine if the rate of change of G is increasing or decreasing. Explain your reasoning for each using features of the graph. So if we look at the graph from 3 to 4, 3 to 4, okay? If I look at little increments, I got too many things going on here. Let me erase my highlighting. I got too many things going on. From 3 to 4. If I do little increments here, if I look at the rate of change, okay, is it increasing? Would the value of those slopes be getting bigger or smaller? Bigger, right? So this would be your rate of change is increasing on this interval. And the reason we could say for this, because if our rate of change is increasing, we could say because F is concave up. Right? Because if our rate of change is increasing, our graph will be concave up. All right, let me erase the rest of those highlights because that's kind of, I will put these dots right here back in. All right, -4 to -3, that's from here to here. So if I look at what's happening here, what about there? Is my rate of change increasing or decreasing? It's a little hard to tell. It looks pretty linear right there, but my graph is decreasing for sure, right? But my rate of change, in this case, is increasing. It's steeper here at that first little segment than it is down here. It's a little hard to tell, but we just said we were increasing over here because F was concave up. Are we concave or up or down here? Or up, right? So we would, again, be increasing. Why is it not letting me draw? Why is it doing this to me? Okay, it's not going to let me write. We're just going to have to talk about it, and you guys can write it down. So, what about from -1 to 1? Rate of change increasing or decreasing? Okay, definitely you're decreasing, you're getting less steep. But what happens right there at 0? You switch to, you don't switch to increasing. The graph starts decreasing, but if we're thinking about the rate of change, right, we've got maybe my slope at first is 1, and then 1/2, and then 1/4, and then I get to 0, and then I go maybe like 1/4, -1/4, -1/2, -1. What's happening to those values? The absolute value of them is going back up. But if I go from 1 to 1/2 to 1/4 to 0 to -1/4, -1/2, -1, it's still decreasing right there. So for 3, it's not letting me write for some reason. 3 is going to be decreasing, and it's because your graph is because it's concave down. It seems like it should be increasing from 0 to 1. It's getting steeper, but it's negative and getting steeper, so those values are becoming more negative. They're decreasing. What about from 1 to 2? Increasing. Reason? Concave up. Okay? So you got increasing for all of those except for 3. That's where you're decreasing. Okay, this is calculator active. We are going to try our best. We're going to run out of time, aren't we? We've done pretty good, though. I mean, we got all of 4 in except for. Let's see if I can get it graphed. It's going to depend on that window. Let's type it in as fast as we can. You can do it if you want, or you can just watch on this time since we are really close to time to go. Okay, hopefully I've got that in right. Alright, I'm just going to hit graph and see what it does to begin with. Okay, so I actually have ended up with a decent graph. My window goes up to 32. I don't know what I was doing before, but I went up to 32. It's only asked, let me show you Zoom Fit on this, because Zoom Fit's what you want to use on this. They gave you a restriction on your domain. They said from 0 to 3, right? So what you want to do, if you have this in, I know some of you are following along, some of you are not. You're going to hit Window. You're going to tell it Xmin 0, Xmax 3. And make sure you hit Enter after both of those. So now, if you do Zoom Fit, which is the zoom button's here in the middle, and Fit is down at the bottom. It's 0, I believe. Yep. It's going to keep those X values from 0 to 3, and then it'll adjust the Y values automatically. And it'll give you a picture of just what you need there between 0 and 3. So you would do Window, Xmin 0, Xmax 3, and then you'll do this. And I want to know when my number of cars in the parking lot switches from increasing to decreasing. Which feature of the graph does that happen at? Where it starts to go down that maximum point that I see right there, right? So on the calculator, that's going to be second trace. I'm going to pick number 4, which is maximum. And then it's going to say left bound and right bound. So I'm going to go up here close to the top of the mountain here. I'm on the left side. I'm going to hit Enter. Then I got to go all the way over the mountain to the other side. And I'm going to hit Enter for my left bound. When it says guess, I'm going to go back up here close to the top. And I'm going to hit Enter. And it's going to tell me the answer, which is, okay, so it's not letting me write. I get 2.44563, 31.89. So which one of those numbers is my answer for this? It says, based on this model, at what time does the number of cars in the parking lot change? It's the 2.445. It is the T in this case. Now, if it had asked what's the maximum number of cars in the parking lot, you would have said 31.89 for that. All right, so I'm going to give you guys 2 worksheets. You can work on them a little bit if you want, but tomorrow, if we don't go over on the assembly, we should be in here for about 45 minutes or so, I think. I may not be here because Hunter is sick. So, but you will have time to work on this, and this is not due until Wednesday. So if you have a busy night tonight and don't touch it, that is fine. Sorry, I'm passing out like, or if you want to work a little on it, it's fine. But if you won't have anything to do tomorrow, you do it all there. So, sorry. All right, there's that. And you should be getting 2 worksheets. One one of them is stapled, one of them is not.
We don't have one for granger on the first one.
There you go. Thank you guys for your attention